Hello, in this video we're going to look at the Nobel Prize in Physics for the year 1902, awarded to Hendrik Lorentz and Pieter Zeeman for the Zeeman effect, in recognition of the extraordinary service they rendered by the researchers into the influence of magnetism on radiation phenomena. We're going to look at the first slide here, and you see here the energy levels of electrons in a situation where there is no magnetic field applied over the place where the electrons are. B is 0, means no electric field. You see the electrons are at this energy level. If you switch on a magnetic field, then you get a split. Some of the electrons which are given here by a downwards arrow go to a higher level of energy, and the other electrons here represented with an upwards arrow go to a lower energy level. And you can see that in the spectrum. If you make a spectrum of a substance, then you switch on, you see a line at which is linked to a certain energy level. When the magnetic field is off, when you switch the magnetic field on, the line splits into two. That's called the Zeeman effect, normal Zeeman effect. Well, first we're going to look a bit at Hendrik Lorentz, his work, why he got the Nobel Prize. Now, during the 1970s, important connections between electricity, magnetism and light were clarified by Hendrik Lorentz. In 1892 he presented his electron theory, which posited that in matter there are charged particles, electrons, that conduct electric current and whose oscillations give rise to light. Lorentz's electron theory could explain the Zeeman's discovery in 1896 that several spectral lines corresponding to the different wavelengths split up into several lines under the influence of a magnetic field. We just saw that. This is coming from the official Nobel Prize site. Here you can see the link to it. You see, Lorentz got it for more than just only an explanation of the Zeeman effect. He did more. Well, then some biographical notes also taken from the Nobel Prize site. This is a summary. Some things are left out. From the starting point of his scientific work, Lorentz took it as his task to extend James Clerk Maxwell's theory of electricity and of light. Already in his doctor's thesis, he treated the reflection and refraction phenomena of light from this standpoint, which was then quite new. His fundamental works in the field of optics and electricity had revolutionized contemporary conceptions of the nature of matter. In 1878, he published an essay on the relation between the velocity of light of a medium and the density and composition thereof. The resulting formula, proposed almost simultaneously by the Danish physicist Lorentz, no relation, you see it's written differently, has become known as the Lorentz formula. Lorentz also made fundamental contradictions to the study of phenomena of moving bodies. In an extensive treatise on the aberration of light and the problems arising in connection with it, he followed Fresnel's hypothesis of the existence of an immovable ether, which freely penetrates all bodies. That assumption was later discarded due to the work of Einstein, for instance. This assumption formed the basis of a general theory of electrical and optical phenomena of moving bodies. From Lorentz stems the conception of the electron. His view that this minute, electrically charged particle plays a role during electromagnetic phenomena in pondering matter, and made it possible to apply the molecular theory to the theory of electricity, and to explain the behavior of light waves passing through transparent bodies. That was new at the time, of course. The so-called Lorentz transformation was based on the fact that electromagnetic forces between charges are subject to slight alterations due to their motion, resulting in a minute contraction in the size of the moving bodies. It not only accurately explains the apparent absence of the relative motions of the Earth with respect to the ether, as indicated by the experiments of Michelson and Morley, but also paved the way for Einstein's special relativity theory. It might well be said that Lorentz was regarded by all theoretical physics as the world's leading spirit, who completed what was left unfinished by his predecessors and prepared the ground for the fruitful reception of the newer days based on the quantum theory. In 1919 he was appointed chairman of the committee whose task was to study the movements of seawater, which could be expected during and after the reclamation of the Zuiderzee in the Netherlands, one of the greatest works of all times in hydraulic engineering. His theoretical calculations, results of 8 years of pioneering work, have been converted in actual practice the most striking manner, and have been seen of permanent value to the science of hydraulics. You see, he did quite a lot. He did even more. If you want to read the complete biographical section, follow the link to the official Nobel Prize site. Here you again see a photo of the Zeeman effect. Literally putting that right. And you see here that this line is taken when the magnetic field is off. And this represents, of course, this is a spectrum. It represents an energy level. And when the magnetic field is turned on, it splits. Here it sits in 5 other lines. And just we saw 2, but it's also possible 3 and 4. Then Pieter Zeeman. During the 19th century, important connection between electricity, magnetism and light were clarified by Hendrik Lorentz. We just saw that. In 1892 he presented his electron theory, which posited that in matter there are charged particles, electrons that conduct electric currents and whose oscillations give rise to light. Lorentz's electron theory could explain the Zeeman's discovery in 1896 that the spectral lines corresponding to different waves split up into several lines under the influence of magnetic fields. You see, it's the same description for why they got the Nobel Prize as with Lorentz. In this case for Zeeman. Again here the official link. Then some biographical information also taken from the Nobel Prize site. Summarized by me, Zeeman's main theme of investigation has always concerned optical phenomena. His principal work was, however, the study of the influence of magnetism on the nature of light radiation, started by him in the summer of 1896, which formed the logical continuation of his investigation into the Kerr effect. If you want to know what that is, look it up, for instance on Wikipedia. The discovery of the so-called Zeeman effect, for which he has been awarded the Nobel Prize, was communicated in the form of papers entitled On the Influence of the Magnetization on the Nature of Light Emitted by a Substance, and on doublets and triplets in the spectrum caused by external magnetization forces. See, in 3 parts. It was originally first published in Dutch, later it was translated into English. The importance of the discovery can at once be judged by the fact that at one stroke the phenomenon not only confirmed Lorentz's theoretical conclusions with regard to the state of polarization of the light emitted by flames, but also demonstrated the negative nature of the oscillating particles. It must be electrons, as well as the unexpected high ratio of their charge and mass, the ratio between electric charge and mass. Thus when in the following year the discovery of the existence of free electrons in the form of cathode rays was established by J.J. Thomson, the identity of electrons and the oscillating light particles could be established from the negative nature and the E divided by M ratio of the particles. The growing number of observations made by other investigators on studying the effects of using various substances as light emitters, not all of them explicable by Lorentz's original theory, the so-called anomalous Zeeman effect, could only be adequately explained at a later date, with the advent of Bohr's atomic theory, so quantum wave mechanics and the concept of electron spin. That was a few years later. Was assembled by him in his book, and him is Zeeman, Research in Magneto-Optics, London in 1913, German translation in 1914. Not only has the Zeeman effect thrown much light on the mechanism of light radiation and on the nature of matter and electricity, but immense importance lies in the fact that even to this day it offers the ultimate means for revealing the intimate structure of the atom and the nature of the behavior of its component. It still serves as the final test in any new theory of the atom. Already in his second communication, Zeeman expressed the opinion that the accepted existence of strong magnetic fields on the surface of the Sun could be verified, since these should alter spectral lines derived from its celestial body, the splitting of the lines. It's typical of Zeeman to extend physical concepts into the realm of celestial phenomena. In a letter to him from 1988, the astronomer G. E. Hale, director of Mount Wilson Observatory, corroborated his opinion by means of photographs, which indicated that in solar vortices the spectral lines indeed appeared to be affected by magnetic field. Well, there's more information on the official site. This is only a summary, as you already have said. Here you see again a photograph of the Zeeman effect, and this time it is taken from a light coming directly from the sun in 1919, as you can see. Okay, then we continue with the award ceremony speech by Professor A.G. Thiel, probably pronounced wrong by me, but okay. It's not very long, so it's almost completely here. Here we go. Since the law of conservation of energy was recognized as the basic principle of modern physics, no realm of that science during the remarkable developments which have been based on this foundation have proved more fruitful than that which has had as its object the investigation of the connection between the phenomena of light and electricity, and of course also magnetism. Faraday, the great founder of the modern science of electricity, suspected this connection and devoted a great part of his experimental research to this very question. This was during the first part of the 19th century. However, Maxwell, that was in the second part of that century, was the first to take up Faraday's ideas again and develop them into a complete mathematical theory. According to this theory, electrodynamic effects are transmitted through space at a finite speed and cause electrical currents, so-called displacement currents, even in non-conductors. Hence, every electrical current of periodically changing direction gives rise to an electrical wave motion, and light consists of just such a wave motion with an extremely short period. This so-called electromagnetic theory of light of Maxwell's at first aroused comparatively little interest. 20 years after its first appearance, however, it led to a scientific discovery which demonstrated its great significance in no uncertain manner. The German physicist Heinrich Hertz then succeeded in demonstrating that electrical vibrations, which are generated under certain conditions when an electric charged body is discharged, are propagated through the surrounding space in a form of a wave motion, and that the wave motion spreads at the speed of light and also possesses its properties. This gave a firm experimental basis for the electromagnetic theory of light. In certain respects, however, Maxwell's theory of light was inadequate, in that it left individual phenomena unexplained. The greatest credit for the further development of the electromagnetic theory of light is due to Professor Lorentz, whose theoretical work on this subject was borne the richest fruits. While Maxwell's theory is free of assumptions of an atomistic nature, thus it doesn't contain the idea of the atom, Lorentz started from this hypothesis that in matter extremely small particles called electrons are the carriers of certain specific charges, electrical charges of course. These electrons move freely in so-called conductors and thus produce an electric current, whereas in non-conductors their movement is apparent through electrical resistance. For instance, at cathodes. Starting from this simple hypothesis, Lorentz has been able not only to explain everything that the older theory explained, in addition to overcome some of its greatest shortcomings. Alongside the theoretical development of the electromagnetic theory of light, experimental work also continued without interruption, and attempts were made to demonstrate in every detail the analogy between electrical wave motion and light. However, it was not sufficient to show a complete analogy between these phenomena. Scientists wished for far more to show that they were identical in nature. From any and to this end attempted to demonstrate that magnetic forces act upon light in the same way as upon electric currents. It is this that Faraday was trying to prove, and the relative experiments carried out by him led to the discovery of the rotation of the polarization plane of light by the effect of magnetic forces. His attempt to demonstrate the influence of magnetism on the radiation from a source of light, the last experiment with which Faraday was occupied, was however unsuccessful. Professor Zeeman has recently succeeded in solving just this problem, which has up till now been the object of fruitless exertions on the part of many perspicacious research workers. Guided by the electromagnetic field of light, Zeeman took up Faraday's last experiment, and after many unsuccessful attempts, finally succeeded in demonstrating that the radiation from a source of light changes its nature under the influence of magnetic forces in such a way that the different spectral lines of which it consisted were resolved into several components, the line splits. The consequences of this discovery give a magnificent example of the importance of theory to experimental research. Not only was Professor Lorentz, with the aid of this electron theory, able to explain satisfactorily the phenomena discovered by Professor Zeeman, but certain details which had hitherto escaped Professor Zeeman's attention could also be foreseen and were afterwards confirmed by him. We see that in the lectures in another movie. He showed in fact that these spectral lines, which were split under the influence of magnetism, consisted of polarized lights, in other words, that the light vibrations are orientated in one particular way under influence of the magnetic force, and in a way which varies according to the direction of the beam of light in relation to this force. Come back to this later. Again, you see an overview of the Zeeman effect. This is the normal Zeeman effect where we talked about, and later also the anomalous Zeeman effect was discovered, and later this was also extended further, of course. For the physicist, discovery, the Zeeman effect, represents one of the most important experimental advances that recent decades have to show. For through the demonstration that light is affected by magnetism in accordance with the same laws as vibrating electrically charged particles, clearly not only has the strongest support been given to the electromagnetic theory of light, but the consequence of Zeeman's discovery promised to yield the most interesting contributions to our knowledge of the constitution of spectra and the molecular structure of matter. Well, that prediction was confirmed. For these reasons, the Swedish Royal Academy of Science has come to the conclusion that the discovery outlined here is of such great importance for the understanding of the connection between the forces of nature and for the development of physical science, that its recognition by the award of the Nobel Prize for Physics is justified. The Academy also bore in mind the great part in which Professor Lorentz has played in the following up of this discovery through his masterly theory of electrons. This is moreover of the great significance as a guiding principle in various other realms. Since the discovery in physics which the Royal Academy of Science wishes to recognize on this occasion represents the result of the most perspicacious research, difficult words, both theoretical and experimental, the Academy considers that the division of the Nobel Prize for Physics between the two outstanding research workers, Professor Lorentz and Professor Zeeman, for the work on the connection between light and magnetism, is not only justified, but just. Well, this is the complete or almost complete award ceremony speech, which you can also find here on the official Nobel Prize site following this link. And as last, you see here a picture of more modern research on the Zeeman effect, in this case with rubidium on the 5F level of electrons. And you see again the splitting of the lines under influence of a magnetic field. It's, yeah, okay. Well, This was the first video on this subject. In a second video, which will be posted a week after this one, we will look at the lectures given by both Lorentz and Zeeman. For now, thank you for watching.